So how to design an inverse class F power amplifier? We have 3 steps. The first step is to use load pool characterization to extract the optimal matching conditions for the fundamental and the harmonic frequencies. The second step is to design the matching network. We use electromagnetic simulation to achieve precise design and to minimize the power loss in the matching network. Here it's very important to minimize this insertion loss, because a very small amount of loss at the output of the amplifier can degrade the efficiency considerably. The final step is to design the amplifier and to tune it precisely in order to achieve the optimal conditions. Here is the load pool characterization setup. It uses a source tuner at the input of the transistor, and what it does, it changes the impedance seen by the transistor dynamically in order to look for the best impedance. We have 2 tuners at the output, one for the harmonic and one for the fundamental. We have biasing circuits at the input and output, a power source at the input, a spectrum analyzer at the output, and all the setup is controlled by software. Here are typical results for load pool measurement. On the top figure, we see the second harmonic and third harmonic. We see the high impedance. Here it's not a perfect open and short, and this is to compensate for the parasitic effects that are present in the device. The figure on the bottom shows the fundamental matching, and with this result, and with using again transistor 10 watt, we can achieve an efficiency of 78.5% at 2.45 gigahertz. Here the design matching network. As we can see, the first stop is for the second harmonic, the second one for the third, and the third for the fundamental, and the second and the fourth is for the fundamental and for biasing. The loss of the matching network is optimized, and out of 32 different configuration structure, we choose the one that presents the lowest loss. Here is an example of inverse class F amplifier designed at 2.45 gigahertz, and the achieved gain is 14.5 dB, and the efficiency is 71.3%. This is the power added efficiency and output power versus input power and versus frequency, and as we can see, achieves a quite good efficiency for bandwidth of about 200 megahertz. This is another example around 1 gigahertz, and for lower frequency, the achieved efficiency is higher, and we can achieve about 81% efficiency. So in conclusion, we provided the different steps to design inverse class F power amplifiers that allow to improve the efficiency in wireless transmitters. And the steps is to use load pool characterization, matching circuit, optimization to reduce the loss, and to tune the matching network after design to achieve the optimal efficiency. And this allowed us to achieve 83% for 1 gig and 74% for 2.45 gigahertz. Thank you.
So the applications are obviously in wireless applications, but are they cell phone technologies? Are they, what areas of application do you see for the power amplifiers that you're working on?
It can be cell phone base stations.
Base stations.
Generally, it's for high power because it's most of the power energy is in the power transmitting capabilities.
So in the end, does this save? It saves a lot of energy, but does it? Is that a battery life issue, or is it just a power generation to a base station issue?
If it can be applied for cell phones, it can improve battery. But the problem in practical implementation in cell phones that implementing linearization technique to compensate for the nonlinear effects of this type of amplification will be not practical for small power devices like cell phones. Generally, the most advantage is when you apply it for base stations, because you can afford to have complex circuit, to have fast signal processors that can compensate for the nonlinearity. And this will result in reducing the power consumption of the whole network, which is the most power in the consumption of the operator. No? Okay, so.